Okay. Okay. Okay, good afternoon to all of you. Is this visible? Is the screen visible?
Yes, sir.
Okay, okay. So you can hear me, audible. Am I audible clearly?
Yes, sir.
Okay, then we'll start. So morning I explained about the types of stresses, tensile stress, compressive stress, shear stress, and about elasticity and plasticity aspects, and strain, lateral strain, linear strain, those things, and Hooke's law with a graph. So graph of stress versus strain. Stress will be Newton per mm square. Strain doesn't have any unit. So initially it will be straight line, then it will be a curve like this, then it comes down. So actually you are going to conduct an experiment on mild steel specimen in your material testing lab. So there tension test, so tensile load is applied on the mild steel specimen, and we are going to calculate the stresses and strain. The stress will be calculated, strain is measured using a strain gauge, and that graph is drawn, and the elasticity is found out. Young's modulus of elasticity is found out by taking the slope of this line in the elastic range. And we discussed about the assumptions made in the simple stress theory. Now the derivation starts. So the first simplest derivation in the strength of materials chapter is this deformation of a uniform bar. So uniform bar means if the cross section don't change over the length, if the cross section remains same over the length, then it is called as uniform bar, or it is also called as prismatic bar. The cross sectional area of bar is same throughout the length, then it is called as prismatic. Otherwise it is called as non-prismatic or non-uniform bar. If it's a tapering rod, then the formula will be different. Now let us see how we can calculate the deformation means extension. Suppose if it is a tensile force, here in the derivation I have taken P as a tensile force acting away from the bar, you can see here. So when tensile force is applied, naturally tensile stress will develop within the body. How to calculate the tensile stress? This P divided by area of the bar, cross-sectional area of the bar will give the tensile stress. Now, once it is subjected to tensile force like this, there will be an elongation of the bar. So, length of the bar will increase. So, L is the initial length, L plus delta L is the final length. So, delta L is the increase in length or change in length. Now, we have to derive an expression for this delta L. Delta L. L you will be knowing, P you will be knowing, A you will be knowing, Young's modulus E also you will be knowing. Young's modulus is nothing but it is the property of that particular type of material. So, for example, if for steel I have given 2 into 10 power 5 Newton per mm square. So, like that for concrete some value will be there, for wood some value, aluminium some value will be there. So, for steel, normally we use, most of the problems we take for steel. That's why 2 into 10 power 5, even if it is not given, you can assume it as 2 into 10 power 5 Newton per mm square or MPa or steel, Young's modulus value. Now here P is the force applied. This force is applied. This is also called as axial force. Please make a note of that. So some of the terms which I am going to explain you may not be there in this. Please make a note of that. So this P is also called as axial force. Axial force means if the force acts along the axis of the member. So if you draw a line at the mid layer, it is called as the axis. So this P is acting along the axis. Or it is also called as direct force. So there are so many words: normal force, axial force, direct force. So force applied is P, L is the initial length, delta L is the length, increased length, A is the cross-sectional area of the bar, so which depends on the type of cross-section. If it is a circular bar, If D is the diameter, pi d square by 4 is area. If it's a rectangular bar, if B is the width, H is the thickness, then B into H will be the area. Then E is the Young's modulus of material of the bar. Now, very simple derivation. Within 2 steps, you will get the answer. So, we are going to get an expression for delta L here. From the definition of stress, stress is sigma, that is equal to P by A. So, force divided by area gives the stress. Strain is epsilon, is nothing but change in length divided by initial length, delta L by L. Now, according to Hooke's law, we know that sigma is directly proportional to epsilon. Stress is directly proportional to strain, or you can write it as sigma is equal to K into epsilon. E into epsilon, where E is sigma divided by epsilon. So, Young's modulus is defined as the ratio of stress to strain within elastic limits. So, the sigma now is substitute for sigma as P by A. Epsilon is delta L by L. That means if you simplify this, you will get PL by AE. Very simple formula to find the extension of the rod, extension of a uniform rod or a bar or a prismatic rod or a bar when it is subjected to tension or compression. What happens even if it is, suppose if the force P is compression, same formula is valid. PL by A is valid. Only thing is the delta L is not extension, it will be contraction. So length will be reduced by the same amount. So PL by AE. So you should remember this formula. For a prismatic bar of length L, area A, Young's modulus E, when it is subjected to a tensile or compressive force of P, its elongation or contraction is given by PL by AE. Please note that units are very, very important. Here, P will be normally, the force will be in newtons or kilonewtons. Please make a note of that. You write down this. So, P will be in Newton or kilonewton. L will be in meter or millimeter. A will be in millimeter square or meter square. E will be in Newton per meter square or Newton per mm square. So, what we do is normally we take P in newtons, L in millimeters, A in millimeter square, E will be in Newton per millimeter square. So, then what happens that Newton and Newton will get cancelled, everything will get cancelled except millimeter. So, you will be getting delta L in millimeters. You can just check that. P you substitute in newtons, L will be in millimeters divided by A in millimeter square, E will be in Newton per millimeter square. If you simplify that, everything gets cancelled except millimeters. So, delta L will be in millimeters. So, if P is tensile force, delta L is positive. Positive means elongation. Please make a note of that. The rod will elongate. If P is compressive, delta L is negative. That is, the rod will contract. For circular bars, a formula I told you, if D is the diameter of the bar, pi d square by 4. That is the area. For rectangular bar, if B is the width, D is the thickness, B into D is the area. So, P divided by this area gives the stress. So, this is a very simple derivation. First derivation in simple stresses and strains in SOM. So, just by taking the definition of stress and strain and using Hooke's law, we can get this. Now, second one, very important here, this is also an important derivation. You have to practice. So, I am going to send this notes to you evening by mail, to the group mail. You can just download it and save it. And practice in a separate notebook, you write down the things, because all the steps will not be there in this. So, I might have skipped some steps here. You have to work those steps. I will explain how to do that. Now, the second derivation is deformation of a circular tapering bar. See, it's very important. For 8 marks or 10 marks, they can ask this derivation. Tapering bar. Tapering bar means cross-sectional area is varying here. So, I have taken here the cross-sectional area is decreasing. It can be increasing also. Now, here I have taken decreasing. So, here the diameter is D1, which is circular cross-section. Here diameter is D2. Length of the bar is L here. Length of the rod or the bar is L here. And I have taken a section here at a distance X. See here, at a distance X from the beginning. And there the diameter I have taken it as dx. Dx is the diameter. So, d suffix x is the diameter. This d small x, dx is the length, elemental length. We call it as elemental length. Total length is L. In that we are going to take an elemental length dx for the derivation purpose. This d suffix x is the diameter at this section. D1 is the diameter here, initial. D2 is the diameter here. That means the diameter is varying from D1 to D2. It is decreasing from D1 to D2 over a length L here. And of course, this force P is a tensile force I have applied. So when tensile force is applied, we have to find the extension of the bar or elongation of the bar. Here also we are finding the expression for delta L, or I can call it as DL. So DL and delta L, they are same. In some derivation, I may use delta L. Here I have used delta L, whereas here I have used DL. Don't confuse, both are same. Even if you write this as delta L, it is correct. So D1, D2, they are the diameters at the ends. L is the bar initial length of the bar. Consider an elemental strip of length dx. See, this is the dx length, elemental strip, at a distance x from A. A is this first point. From the point A at a distance x, I have taken a section here. Let the diameter of the strip be dx, d suffix x. Don't confuse with dx with d suffix x. D suffix x is the diameter, dx is the length here. So A suffix x is the area of the strip here. Here the area of the strip, which is once again pi dx square by 4. Now the general, if you consider a small length here, this can be taken as a uniform rod. For this small length, it can be taken as a uniform rod. That is the purpose of taking a small length dx, elemental length. We call it as elemental length dx. When you take elemental length small dx, this diameter variation can be neglected, so that you can make these two diameters almost same. When dx is very small, the difference in the diameters at these two sections will be very, very small, so that you can consider it as a uniform rod only. When you take that as uniform rod, what happens? Deformation of this elemental strip. If you take a uniform rod, the formula is PL by AE. PL by AE is the formula just now we have derived here. So this is the formula we are going to use for uniform bar. If you assume the smaller length is of uniform bar, then what happens? Deformation of elemental strip, I will write it as DLX, because for this elemental length dx, I am finding the extension. So DLX is for this small length. It is given by PL by A is the formula. Here L becomes dx. L becomes dx divided by A becomes AX, because I am taking the area here, into E. So E and P, they are same, because this P is acting here also, here also. At all the points, the force is P only. So P into, instead of L, it is dx, divided by, instead of A, it is AX, into E. Now, if you want the elongation of the total length of the rod, total length, then we have to integrate. That's why we are using this dx term here. So integration of this will give the total extension of the bar. So total deformation of the bar is denoted by delta L or DL. So DL is integral of this DLX. So if you integrate this between the limits 0 to L, why it is 0 to L? The variable of integration here is x. X can vary from 0 to L here. So x is 0 here, because this section is taken from the point A. At the point A, x is 0. At the point B, so this suppose if I take this as B, x is equal to L. So x can vary from 0 to L. So if you integrate this between the limits 0 to L, you are going to get the total deformation of the bar. Now what happens here? P into dx divided by AX is nothing but pi dx square by 4, because that is the area at that section. Diameter at that section is d suffix x. So pi dx square by 4 is the area at that section, into E. So now here, if you simplify that, what happens? This 4p by pi e, it becomes 4p by pi e into integral of dx divided by d suffix x square. Like that you will get. So if you simplify that, what happens? See, if you are integrating this 1 by dx square, you have to integrate here 4p by pi e, that will be there here, into integral of 0 to L dx divided by d1 minus kx. So why it is d1 minus kx? So we have to get an expression for dx by interpolation. So you see this diagram. If you take here, if I want to write the expression for dx in terms of d1 and d2, in terms of d1 and d2, so this is the expression. So it becomes dx square becomes d1 minus kx whole square. So here you can see here, I have written here some figure here. So this is at this end, at the end A, if you take the radius is d by 2. If you want similar triangles, you have to take the half the portion of the bar. So it is d by 2 here, it is dx by 2 here, it is d2 by 2 here. So d1 by 2, dx by 2, d2 by 2. So if you construct a similar triangle here, so you have to take a similar triangle here, and if you introduce a constant k here, so I have done here all the steps I have done here. You can just go through this. So using similar triangle principle, so you will be getting a constant. This constant k is nothing but d1 minus d2 divided by L. Like that you will get. So here what happens? So if you use that constant k here, so that dx can be written as d1 minus kx whole square, and then afterwards you have to integrate this term. So 1 over d1 minus kx whole square you have to integrate, and then if you integrate and simplify, finally ultimately you'll be getting this expression. So for a tapering circular rod, the deformation is given by 4PL divided by pi E into D1 into D2. So this notes I am going to send you today evening. So you can just check it up how it has been done. So this formula also you should remember. That means once you know the initial diameter, final diameter, length of the bar, force applied and the Young's modulus, you can compute the change in length of the bar or increase in length of the bar. If P is tensile, delta L is positive. If P is compressive, delta L is negative. Okay, that means positive means it is extension, negative means it is contraction. That is the meaning. That's all. Okay. Now, that is one derivation, that is circular arm. So you have to practice this. How you got this d1 minus kl? What is that k there? So all those things I have written there by the side. You can just go through that. Yes, yes. Dx I have taken it as d1 minus kx, like this. See, this is d1 minus kx. So how you got that, I have explained here by using similar triangle principle. You have to draw a line here, compare this bigger triangle with this smaller triangle, take the ratios of the corresponding sides. They should be equal. That is the property of a similar triangle. That's what I have done here. Using this, I have got an expression for dx as d1 minus kx. That I have used here. And afterwards, I have substituted for k, and we got the final answer like this. After substituting for k, you can just try this. You can just try this substitution and all. Final answer is this. This is a very important derivation. Next, coming to another derivation. See, here it is a rectangular rod. So it is also tapering, but cross section is rectangle here, not circular. It is a rectangular rod. In the case of rectangular rod, instead of diameter, you will be having a width and thickness. Of course, here I have taken constant thickness. See, thickness of the rod I have taken same. Width of the rod is changing here. So this B1 is the width here, B2 is the width here, Bx is the width at some distance x. Similar figure, but here in the last one, it is circular cross section. Here it is rectangular cross section. Their diameter will come. Here width will come. So this is B1, B2, Bx. They are all the widths. T is the thickness. Thickness is constant here. Please note that thickness of this rectangular bar is constant. It is subjected to tensile force P like this, tensile force P like this. So L is the initial length. So due to tensile force, it gets elongated. So delta L is the increase in the length. Now I have written here B1, B2. They are the widths or breadths at the two ends. Length of the rod is L. Thickness of the rod is T. So it is constant T. Then what you can write for if you want the area here is B1 into T. Area here is B2 into T. This force P is acting over this area. Okay, B2 into T. Here area is B1 into T. Here the area will be bx into t. So b suffix x into t. That is your ax here. So from here also, from similar triangles, if we take whatever we have done here on the same lines, instead of dx, it is bx here. So you will be getting same thing. Bx is equal to b1 minus kx. Here we are getting dx is equal to d1 minus kx. Here we are getting bx is equal to b1 minus kx. So once you get this, if you use the same principle here also, by considering a small elemental length dx here and applying the formula for uniform rod, so you will be getting dlx as p into L divided by A into E. That is the formula. So here L is dx, A is ax. So now substitute for ax as bx into t. So the dx will remain same. If you want the elongation of the entire rod, it is integration of this. That's what I have written here. dl or delta L will be the integration of this. So integration of this is, so P is as it is. So what happens, this T you can take it outside because it is constant. So P is constant, you can take outside. T is constant. E is also constant. Young's modulus also is constant. So variable is x here. So we have to integrate dx divided by b1 minus kx. So if you should know the integration formula, the integration of 1 over, it is like a minus bx, something like that. Integration will be log. So that is minus 1 by b into log of that a minus bx. So that is the integration. So integration formula you should be knowing. Otherwise you cannot substitute here. So you should know the formula for integration. So integration of 1 over a minus bx, like that it is there. So its integration is minus 1 by b into log of a minus bx. So that is how it is written. So between the limit 0 to L, because x can vary from this end to this end. At this end x is 0, at this end x is equal to L. So x can vary from 0 to L. That is the concept. So if you integrate and if you simplify all these things, finally you will be getting this formula. So this formula also you should remember. Please note that for circular rod, elongation is given by this. Circular tapering circular rod, elongation is given by 4pl by pi e d1 d2. Formula you should remember. If they give a problem, we should directly substitute that. For a rectangular rod, tapering rectangular rod, this is the formula. PL divided by T into B1 minus B2. B1 is the width at one end, B2 is the width at the other end. So larger value is taken as B1, smaller value is taken as B2, then log B1 by B2 to the base E. So this is the formula to find out the elongation of a tapering rectangular rod. So we have discussed about three types of bars. Uniform bar, it can be circular or rectangular or square, whatever may be the shape, cross-sectional area remains same. In that case, elongation is given by PL by AE, that's all. In the case of circular tapering rod, whereas the cross-sectional area is decreasing or increasing, cross-section is circular, then the formula is 4PL divided by pi e d1 d2. So you should be knowing the notations. Please note that units are very, very important. Normally P will be in newtons, L will be in millimeters, E will be in Newton per millimeter square, D1 and D2 will be in millimeters. Please make a note of that. then DL will be in millimeters. Answer will be in millimeters, elongation. Similarly, here the formula for tapering rectangular rod, formula is this. Here also P will be in newtons, L will be in millimeters, T thickness will be in millimeters, E Young's modulus will be in Newton per millimeter square, B1 and B2 will be in millimeters. Here also B1, B2 will be in millimeters. This is a number. So final answer is DL will be in millimeters. So there are three important formulae here. So you have to practice all the three. The first one is very simple, PL by EE for any shape, but it should be uniform bar. That is prismatic bar. It can be circular, rectangular, or square, any shape. Where next two different derivations are tapering circular. So diameter is increasing or decreasing, it is not constant. Then the formula is this. Okay. Then rectangular tapering. So cross section is varying, thickness is constant, but width is varying. In that case, the formula is this elongation of a tapering rectangular bar. So these three formulae you should remember because they may give problem also. If there's derivation, you can do like this, or if they ask a problem, then you should be knowing the formula. But units are very, very, very important. Once again, I am telling you, P will be in newtons, L will be in millimeters, T will be in millimeters, E will be in Newton per millimeter square, B1, B2 will be in millimeters. So these are the three important types of cross sections normally we come across. Now the next one is with varying cross sections. See, there are varieties of problems. So don't think that you will be having only one type, that is circular, only rectangular, like that. Variety. So here, suppose sometimes what happens, bars with varying cross sections. So see here, in this arrangement, this is a circular bar only, but it is varying like this. For this portion, L1, length of the bar is L1, diameter is D1. It is uniform bar only, but from here to here it is uniform. Next, from here to here is separate diameter. From here to here, separate diameter. So L1, L2, L3, they are the lengths of the bars. D1, D2, D3, they are the diameters. Circular rod only, but it consists of three portions. Three elements you can call. So these three are called as three elements of in the bar. So in that case, suppose if the entire system, all the three bars together, put together, they are, you can call it as a composite bar also. You can have that word composite bar. You can add that word composite bar. So when this P is applied on this composite bar, so D1, D2, D3 are the diameters, A1, A2, A3 are the cross-sectional areas. So the cross-sectional area of this will be pi d1 square by 4. Cross-section area of this will be pi d2 square by 4. Cross-section area of this will be pi d3 square by 4. So all the areas will be in millimeter square once you substitute diameter in millimeters. So L1, L2, L3, they are the lengths in millimeters. Okay. P will be newtons or kilonewtons, let us say. Now, in such a case, how to find the total deformation? So in such a case, what happens, see here, all the bars are subjected to same force P. So all these three, 1, 2, 3, if I call this as 1, this as 2, this is 3. So all the three portions of the bar, 1, 2, 3, they are subjected to same force P. Length are different, areas are different, but force is same, and of course E value also is same. E value means it is Young's modulus, that is modulus of elasticity of the material. So it is of same material. So entire bar is made of steel or aluminium, anything, same material, but diameters are different. Length and diameter they vary. So E value remains same. So all the bars are subjected to same force P. Delta L1, delta L2, delta L3, they are the deformations. So delta L1 is a deformation in the first portion, delta L2 second portion, delta L3 third portion. If you want the total deformation, we have to add the deformations of all the three portions separately. So delta L1 plus delta L2 plus delta L3 gives the total deformation of the composite bar. It is called as composite bar. In that case, see here, delta L. So if you substitute for delta L1, so this first portion is a uniform bar. Formula is PL by AE. So PL by AE is the formula for finding the elongation of a prismatic or a uniform bar. So L is replaced by L1. P is P only. So P into L1 divided by A is replaced by A1 into E. See, I have written here P into L1 divided by A1 into E. Similarly, for the second portion, P force P is same. Area becomes A2 here. A length becomes L2 here. So it becomes PL2 by A2 into E. Plus, for the third portion, it is PL3 by A3 into E. What is A1, A2, A3? They are the areas. So A1 is pi d1 square by 4. A2 is pi d2 square by 4. A3 is pi d3 square by 4. So if you observe this expression, here P and E, they are constants. You can take it outside, common. You can take it common. So P by E, if you take common, so you'll be getting L1 by A1 plus L2 by A2 plus L3 by A3. So like that, even if number of bars, if some more bars are there, you can just go on adding that. One more portion is there means you have to take in one more term will come here L3 by L4 by A4, L5 by A5 like that. So this P by E remains same. So this is another type of problem wherein same material is there, same force is applied. So force is same, material is same. Force is same means P is same, material is same means E is same. Diameter and length they are varying. So you have to apply that uniform bar formula individually for all the portions and we have to calculate. That is the meaning. So here force is tensile force. Entire all the three bars will elongate. Total elongation we have to add. Here another example I have shown here. You can see here there is a second one is tapering circular. So D1, D2. If they give D1, D2, it is circular. Okay. If they give B and T, suppose if they give as B this one and T thickness and width if they give, it becomes rectangular. Here only diameter if it is given, then it is circular. So D1 is here. Here also D1 is there. This becomes D2. So this is D1, this is D2, and this is D2. So uniform bar, tapering bar, uniform bar. If you want the total elongation for this case, we have to add the deformations due to all the three portions. See, due to the first portion, suppose if I take this as L1, I have not written here. Please make a note of that. From here to here it is L1. From here to here it is L2. From here to here it is L3. So deformation of this first portion is PL1 by A1 into E. What is A1? A1 is pi D1 square by 4. L1 is this length. Please make a note of that. L1 is this length. L2 is this length. So this since is a tapering circular rod, we have to use the second formula. 4PL divided by pi E D1 D2. Here L is replaced by L2. That's all. L2 is the length of this member. Next, this is L3. L3. So P into L3 divided by A3 into E. So here there is no question of A2 here. So instead of that, you will be having the formula like this. Whereas in this portion, you will be getting A1 as pi D1 square by 4. Here A3 is pi D2 square by 4. So once you know the values, you can just substitute and simplify. So please be careful whether they give uniform bars together or uniform bar combined with tapering bar. We have to add the deformations due to all the three. And another thing here, please make a note here. This I have shown compressive here in this, whereas here I have shown tensile. So the difference between these two is here I have shown tensile. Away from this, elongation will take place, whereas here I have shown compressive force. If I show compressive force, the meaning of that is instead of elongation, contraction will take place. So this length will reduce, diameter will increase for this bar, for this entire bar. So whatever delta L you are going to calculate, that is nothing but decrease in length. Okay. Whereas in the first case, if tensile force is there, formula is same, but you are getting increase in length. If compressive force is there, same formula, you are going to get decrease in length. So this delta L in this case is decrease in length because it is a compressive force. P is applied like this, See the arrow. Arrow direction is very, very important. So if you apply that in the compressive direction, you will get contraction of the bar. So this is what I wanted to explain. Here, this is how the problem will be. Calculate the deformations in each bar and the total deformation. Also find the stresses in each bar. So take E is equal to 2 into 10, E, this is E. E is equal to 2 into 10 power 5 Newton per mm square or MPa, megapascal. That is steel. For steel, that is the value of E. Now you can see in this problem, he has given three portions. The first portion 150 millimeter diameter, second portion 100 mm diameter, third portion 200 mm diameter. Tensile force is given 100 kilonewton. And the first length portion is 200 mm, second length portion is 150 mm, third length portion is 250 mm. L1, L2, L3, D1, D2, D3, P is 100 kilonewton. That's all. Now in this case, this belongs to this type. See, first one, yeah, this type of problem. So you know all the values. P is 100 kilonewton. See, P is 100 kilonewton. For the first one, elongation is given by P into L1 divided by A1 into E. So what is A1? A1 is nothing but pi d1 square by 4. For a circular rod, area is pi d square by 4, pi d1 square by 4. So d1 is 150 mm here. So substitute that. So pi into d1 square by 4. So this 100 kilonewton, I have converted it into Newton. So if you convert into Newton, it becomes 100 into 10 cube. Kilonewton means 1 kilonewton is 1000 Newton. So 10 cube means 1000. So 100 into 10 cube into 200 mm is the length. So bar length is 200. The portion is 200 mm divided by A1 is pi d square by 4. D is that is 150 into E value 2 into 10 power 5 Newton per mm square. You should be very careful about the units. That's what I told. Force you keep it in newtons, diameter you keep it in millimeters, length you keep it in millimeters, area will be in millimeter square, Young's modulus E value will be in Newton per millimeter square, then your delta, that change in length will be in millimeters. So if you simplify this, you will get 5.6588 into 10 power minus 3 millimeter. So this is the elongation in the first portion. So this rod, this you will elongate by this much, very small value. See. Similarly, if you take the second bar, if you take the second bar, formula is same because it is uniform bar only. The thing is L2 is 150 mm, D2 is 100 mm. Formula is PL2 divided by A2 into E. So P remains same here, 100 into 10 cube into L2 is the length is 150 mm here, divided by pi D2 square. D2 is 100 mm, pi D2 square by 4 into E value 2 into 10 power 5. That is remains same. So if you simplify that, you will get this much. Next, for the third portion, PL3 by A3 into E. So that is given by 100 into 10 cube into 250. Numerator is same, not same. L is 250 mm here, divided by pi into D3 square by 4. So D3 here is 200 mm. So D3 square by 4 into E value is 2 into 10 power 5. So you are going to get delta L3 as this much. So these are the values of elongations in each portion separately. That's what he has asked. Deformations or elongations in each bar. Then total deformation you have to add. Because all the three bars are stretched here, elongation takes place, there will be an increase in length. That increase in length, total increase in length is the sum of all these three, which is, if you add, you are going to get this much, 0.01918 mm. You are going to get this much. Now he has asked the stresses in each bar. How to get stress value? So stress value is given by force divided by area. Simple. So force here is P only. In all the three portions, force is P only, that is 100 kilonewton. Areas are different. Area of this will be different, that is A1. A1 is pi into 150 square by 4. A2 will be pi into 100 square by 4. A3 will be pi into 200 square by 4. So areas are different, force remains same. So P by A1 is this value. P is once again 100 into 10 cube in newtons, divided by A1 value is pi d1 square by 4, which has been kept. This is your A1 value, pi into 150 square by 4, which is after simplification you will get this value. So this is the stress value will be in Newton per mm square. Please note that the stress value will be in Newton per millimeter square, because the force is in Newton, area is in millimeter square. So Newton per mm square. Similarly, stress in the second portion is P by A2. We have to take area of this portion. P remains same. force is same here. So P by A2. A2 is what? Pi into 100 square by 4. This is A2. See here. So that if you simplify, you will get this much. If you divide that, you will get this. This is the value of stress in the second portion. In the third portion, sigma 3 is P by A3. So once again, P in newtons divided by A3 is nothing but pi into 200 square by 4. This is A3. If you simplify that, you will get this much. You will get this much, and the stress is this. So if you observe these values, what you can say is, as the area increases, stress reduces. See here. For this, if the force is same here, P is the force, it remains same in all the three portions. But if you see the diameter and the area, so here the area is less here. When the area is less, area is in the denominator, so your stress will increase, 12.4 here. Here, this area is more here, 31,415 in the denominator. So when the area is more, stress will be less. You can see the values here. So in this problem, force is same, diameter is different, length is different, Young's modulus is same. So P and E, they are constants, whereas length and area are variables. So he has asked deformations in each bar as well as the total deformation. So like this. Suppose if the force P is compressive force, then delta L is negative and we have compressive stress. That's all. So if suppose in the same problem, if they give 100 kilonewton like this, 100 kilonewton like this, and here also 100 kilonewton like this, it becomes a compressive force. When it is compressive force, compressive stress will be developed. Instead of elongation, you will be having contraction. That's all the difference. Formula remains same. Only thing is, instead of elongation or extension of the bar, if it is compressive force, contraction of the bar will take place. So length will reduce. So this is a simple exercise problem in which we have calculated deformation in each bar as well as the total deformation. So today, I think I can stop here. You have to go through this. I will send you the notes to the group mail today only. You just download it, and whatever steps are I have explained here, you have to practice. So you have to write the diagrams, everything. Don't keep as it is, because this subject we need lot of working. That means strength of materials, one of the tough subjects. So you have to, more you work, better you will get the marks, because it is like mathematics. That means derivations will be there. Numerical examples are more. As I already told, no theory here. So only 10 marks you may have theory. All are derivations and numerical problems only. You have to cover 5 modules. It's a actually 5 hours 5 hours subject. This is so. In online class, I think they have given 4 hours, but in offline class, it carries 5 hours, out of which 3 hours lecture, 2 hours tutorials, like that. So totally 5 hours in a week, we have to work on this. It's a very, very important subject to learn the future subjects, structural analysis, design of RCC, design of steel structures, design of pre-stressed concrete structures. All analysis and design subjects, they depend on the fundamental concepts of strength of materials. So you should be strong in mechanics and strength of materials. Then only you can do well in structural analysis subjects. So concentrate on whatever I am going to explain in the class. Don't be absent, because if you become absent for 1 or 2 classes, you may not be in a position to understand the concepts in the next class. So because all the stress strain from the beginning class only, you should understand. So you can refer that strength of materials by Bhavikatti, strength of materials by mechanics of solids of strength of materials by R.K. Bansal is also there. And some more books. There are a lot of books. I think one more. I think Keshava sir also has written one book. Keshava and Dr. Arun Kumar. Some 3-4 authors are there. So one of the others is Keshava sir. That book is also there. I think you can refer that also. Numerical problems, you have a lot of problems have been done. Worked problems will be there. So only thing is you should, and Basavarajaya, that book is also good, strength of materials, Basavarajaya. So a lot of numerical examples have been worked out. Exercise problems will be there. More you work, better you will understand. So that's why if you attend the class, concepts you can easily understand. Then you can do any number of problems because in notes what I have prepared, I have covered most of the problems. But number of problems you should work. That should be more. Then only you will be thorough with. You will be having a grip on the subject because it is not a theory subject, so you should concentrate more on the derivation and the numerical examples. So tomorrow I will be continuing with the take the attendance. So 19 batch were all present. 19.
So 002.
002, correct. Then
003.
003. Then
005.
005. Okay, then
006, sir.
6. Okay. Then
007, sir.
7. Okay. Then after 7, 8 is there.
010.
010. 008 is not there. Okay. 010. Then 0. After 010. 011. Yeah. Then after that
016, sir.
016. 016. Yeah. Then
017.
017. Yeah. Then
018.
018. Then
Sir, 019.
019. Yeah. Then
Sir, 021.
021. 021. Morning you are absent, huh? Why you are absent?
Sir, network issues, sir.
ಎಲ್ಲಿದ್ದೀರಾ ನೀವು?
Sir, ಊರಲ್ಲಿ.
ಯಾವ ಊರು? ಅದೇ ಊರು ಗೊತ್ತು, ಯಾವ ಊರು ಅಂತ ಕಾಡಲ್ಲಂತೂ
ಕನಕಪುರ, sir.
ಇರಲಿಲ್ಲ. ಕನಕಪುರನ? ಕನಕಪುರ ಟೌನ್ ಅಲ್ವಾ ಮರಯ? ಅಲ್ಲಿ ನೆಟ್ವರ್ಕ್
Sir,
ಇರಲಿಲ್ವಾ?
ಸರ್
ಹೌದಾ?
ಬೆಳಿಗ್ಗೆ ನೆಟ್ವರ್ಕ್ ಸಿಗ್ತಾ ಇರಲಿಲ್ಲ ಸರ್ ಜಿಯೋದು.
ಹೌದಾ?
ಹಾ,
ಓಕೆ, ನಾನೆಲ್ಲ ಈಗ ನಿಮ್ಗೆ ಇದ್ ಮಾಡ್ತೀನಿ, ಮೇಲ್ ಕಳಿಸ್ತೀನಿ ಆಯ್ತಾ? ಸಂಜೆ ಈ
ಹಾ,
ನೋಟ್ಸ್
sir.
ಎಲ್ಲ ಮೇಲ್ ಕಳಿಸ್ತೀನಿ, ಎಲ್ಲ ಸ್ಟಡಿ ಮಾಡ್ಬೇಕು. ನೀವು ನೋಟ್ಸ್ ಮಾಡ್ಕೊಳ್ಳಿ ನೀವು. ಮತ್ತೆ ಕಾಲೇಜ್ ಸ್ಟಾರ್ಟ್ ಆದಾಗ ಫಾಸ್ಟ್ ಅಲ್ಲಿ ರಿವೈಸ್ ಮಾಡ್ತೀನಿ, ಎಲ್ಲ ಫಾಸ್ಟ್. ಗೊತ್ತಾಯ್ತಾ?
ಹಾ, sir.
ಶತಾಬ್ದಿ ಎಕ್ಸ್ಪ್ರೆಸ್ ಎಲ್ಲ ರೆಡಿ ಇರ್ಬೇಕು ನೀವೆಲ್ಲ. ಅಲ್ಲಿಗೆ ಎಷ್ಟು? 1 2 3 4 5 6 7 8 9 10 11 12. ಇನ್ನಿಬ್ರು ಯಾರು? another 2 are there, total 14. who is left out?
ನಿಮ್ದೇ ಸರ್ ಇನ್ನೆರಡು.
021 ಆಯ್ತು. ಇನ್ನು ಯಾರಿದ್ದಾರೆ? 18 ಬ್ಯಾಚ್ ಯಾರು ಇದ್ದೀರಾ? 18 ಬ್ಯಾಚ್.
ಸರ್ 2 ಅಕೌಂಟು ನಿಮ್ದೇ.
ಹೌದಾ? 2 ಅಕೌಂಟ್ ಇಲ್ಲ ಮರೆ, ನಂದು 1 ಅಕೌಂಟ್ ಅಲ್ವಾ?
ಅದೇ ಸರ್,
ಒಂದ್
ಒಂದು
ಕ್ಯಾಶ್
ಸ್ಕ್ರೀನ್
ಆಗುತ್ತೆ
ಮತ್ತೆ
ಸರ್.
ಒಂದು ರೆಕಾರ್ಡ್
ನೀವು
ಮಾತಾಡೋದು ಸರ್.
2 ಬರುತ್ತೆ ನಮ್ದು. ನೀವೆಲ್ಲ ಭಯಂಕರ ಬುದ್ಧಿವಂತರಿದ್ದೀರ, ನಮ್ಗೆ ಗೊತ್ತಾಗಿಲ್ಲ. ನಿಮ್ಮನ್ನೆಲ್ಲ ನೋಡ್ಲಿಕ್ಕೆ ಆಗ್ತಾ ಇಲ್ಲ, ಬರೀ JSS APS ಅಂತೆಲ್ಲ ಬರ್ತಾ ಇದೆ. ನೀವೆಲ್ಲ ಸ್ವಲ್ಪ ಮುಖ ತೋರಿಸಿ ನೋಡೋಣ ಒಬ್ಬೊಬ್ಬರಾಗಿ. ತೋರಿಸ್ಬೋದಲ್ಲ ವಿಡಿಯೋ? ನೋಡ್ಲಿಕ್ಕೆ ಅಲ್ವಾ
ಸರ್? ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್ ನಲ್ಲಿ ಸರ್.
ಎಲ್ಲ ಹೇಗೆ ಅಲ್ಲ, ಎಲ್ಲ ಇದಾಗಿದ್ದೀರಾ. ಆಯ್ತು, ತೊಂದರೆ ಇಲ್ಲ. ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ನಾನು ಮುಂದೆ ಪ್ರಾಬ್ಲಮ್ಸ್ ಮಾಡಿಸ್ತೀನಿ. ಕಂಪ್ಲೀಟ್ ಪ್ರಾಬ್ಲಮ್ಸ್ ಇದೆ ನೆಕ್ಸ್ಟ್, ಆಯ್ತಾ? ಮಿಸ್ ಮಾಡಬೇಡಿ ಕ್ಲಾಸ್, ಗೊತ್ತಾಯ್ತಾ? ಓಕೆ, ಗುಡ್ ಲಕ್, ಹ್ಯಾವ್ ನೈಸ್ ಡೇ.
Thank you, sir.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು.